Yeah, today I'm going to talk about the water generation from solar wind and micrometeor impacts on the moon. This was done in collaboration with our collaborators listed here. Before I get into that, I kind of want to talk about latitude dependence actually and how weird it is actually. So we've seen this picture before. This is from Schweiri's work. Numerous other people have documented this well. It's not a controversial thing to say that there's more hydrogen towards the poles, right? And so first glance, you might think, oh, that makes sense. It's colder up there. It must retain more hydrogen. But, you know, when we start to think about it from the chemistry perspective, it's a little strange, actually. So there's been numerous experiments that have documented that hydrogen implantation will generate these hydroxyls, right? It is a, and if it's showing up in infrared spectra, it's a chemical bond, it's stable. The reverse reaction is not going to happen. So when flux is dominant at the equator, so we should see more at the equator as well. And then finally, if it's stable, then it should also diffuse into the bulk as well, and that should increase the concentration by orders more of magnitude than what we're seeing. So without a loss term for that MOH, we really kind of should see this inverted trend where the peak is actually at the equator. So why is diffusion into the bulk limited? That can be kind of explained. So Schweili talked about this or hinted at this a little bit. So radiolysis actually decreases that activation energy. It allows for diffusion within that radiation zone to be easier, right? Right below that, in the pristine bulk material, you have a high activation energy diffusion, so that creates this kind of boundary where that's not just going to happen. And then if you take into consideration the surface removal process called recombinant desorption, which we'll talk about more of that later, you have this concentration gradient then, which drives transport of those hydroxyls to the surface. And so that is, you know, selectively moving them to the surface and not into the bulk, which can explain why we don't see as much in the regolith. Okay, so the model is relatively simple. I've talked about this before, but I did modify it a little bit to include diffusion. So hydrogen can implant, make these hydroxyls. Those hydroxyls can then diffuse into the bulk or to the surface, where they can then react to form water. So the higher temperature occurs, there's a higher probability of water forming, right? So as you can imagine, during an impact event, the temperature is quite high, so this reaction rate is also quite high. In addition to that, you also have oxygen from solar wind, and that can help replenish some of the oxygen that is removed during the water formation process. That can, again, diffuse in the bulk into the surface, and the process just kind of repeats itself. Now, it's not necessarily this kind of cyclical process, it is happening simultaneously, right? So from that very simple model, you get these relatively complicated differential equations are all coupled together. You know, I'm not going to go into detail for these, but for this to be solved, you need the rate constants, right? And a lot of these can be got from experimental work. So like Micah Scheibel's work can tell us what the rate constant is for proton implantation. But the diffusion one was a little trickier, and we had to use Fick's law to kind of approximate that. So I'm not going to talk about this plot on the left, but Fick's first law, for those who don't really remember this, the flux is just proportional to the concentration gradient. I multiply that by the area, that tells me the rate of molecules going to the surface. I can approximate that slope by linear approximation. And then I can also get the similar equation from rate kinetics, and then I can get finally a rate constant, which allows me to solve those differential equations. So this is what our collaborators gave us. This is sort of an updated melt rate, kind of expanding on that Centella paper. This is a snapshot at full moon. So there's just two things to really notice here is that the peak melt rate is a little offset from the subsolar point, and that the overall melt rate is pretty low. So on the order of femtograms per centimeter squared per second, right? So it's not really generating a lot of water, but over geological time periods, this does contribute a pretty significant amount. Finally, some of the results. So on the left is the activation energy of 0.52 eV. This is based on some experimental work. And then on the right is just an arbitrary value of 0.8 eV that I chose just to do some parameter searching. The top is water from recombinant absorption, bottom is from impact melt. And you can see that the overall trend is very similar. So you have to build up those hydroxyls, then eventually you start burning them off. And then there's this decay. That decay is actually from a loss of oxygen. So that decreases the availability for hydrogen to bond to, right? The main difference between the high and low case is the time that it takes to get to that peak, right? So in the low case, the peak is around 2,500 lunar days. The high energy case, that peak is around 9,000 lunar days. And then also there's the ratio between the two. So the low energy case, the dominant process is recombinant desorption. On the high activation case, it's actually about 1-to-1. And that can be explained simply by the fact that hydrogen is in the bulk for longer periods of time, and that it is now being more converted into water during that impact melt event. This just kind of shows us the progression of water, similar to that peak or plot that we just saw, but this is a function of latitude and longitude. Snapshots at full moon. So early on, we have most of the hydroxyls in the equator, so you expect more water to be formed there. But two things begin to happen: that loss of oxygen that I talked about, and that also the hydroxyl concentration needs to increase to compensate for the colder latitudes, right? So you end up with this kind of progression of peak water formation towards the poles. Eventually, however, around 75 degrees, recombinant distortion just shuts off completely. But you're still, those high latitude regolith grains are still being implanted by protons. And so what you end up with is the dominant impact melt process where water is being formed in the polar regions for an old regolith surface. So in addition to calculating where water is made, we can figure out where water goes. And this is just basically from a simple ballistic hot model that takes into account photodissociation, dissociative absorption, sputtering, Jean's escape, all the typical loss terms. And you can kind of see that you get what do you expect, right? So the cold latitudes have more water, and there's a small diurnal variation as well. And then in addition to that, we can calculate the average accumulation rate for the permanently shadowed regions. And based on that number, I get about 0.5 million years to get to that 5% weight target. Now that is incredibly short, but I'd also like to point out that this doesn't take into consideration any impact gardening, right? So that is going to severely diminish that rate by quite a lot, actually. And then finally, what good is a model without the ability to compare with some observations to benchmark it? On the left is the Honeyball data set. On the right is a LAMP data set from Hendricks et al. And you can see it matches fairly well, especially the diurnal trend on the LAMP data. The dusk kind of terminator point on the later times in the bottom here, the Honeyball set, we're underestimating the water that's being produced, and that could be from the micrometeor impacts. So by this time, that flux is getting more towards the night side. And so if there is more water being generated in that process, it's going to be immediately condensed on the night side, which can explain that discrepancy right there. So in summary, the radiation zone allows for transport within much easier in that zone and inhibits diffusion into the bulk, especially when you couple that to a surface loss. The latitude dependence is most likely a combination of OH and water, since the warmer latitudes remove both of those. If there is a longitude or diurnal dependence, it's possibly adsorbed water, since the solar wind flux doesn't mass balance with the observed 100 parts per million change that we've seen. And then impact gardening tends to wash out the surface relatively quickly, so on the order of 1,000 years, right? So that kind of implies that there is a low activation energy of diffusion to give you that latitude dependence that we see. And then finally, the activation energy for the diffusion ultimately controls the ratio of water made from RD to impact melts. And with that, I think I'm slightly over, so I'll just end and take any questions. Thank you.
Okay, we have time for one brief question. And just as a quick reminder, please introduce yourself and your institution when you ask a question. And no one is running to the mics. So Paul Lucy online has a question. What is the water concentration in the exosphere resulting from this model? And does it agree with LADI?
Yeah, that's a good question. It's a little high, but on the order of about 100 molecules per cubic centimeter. So it's definitely, a couple orders of magnitude more than the 0.6 molecules per cubic centimeter that Bennett came up with, which to be honest, I think is actually kind of low.